All right, this is going to be our walkthrough for the homework assignment titled Applications of the Derivative Multiple Choice. So this is just old AP test questions. Most of them are just straight up old AP tests or practice AP tests. A few of them are ones that I made up myself, but regardless, these will be good practice for you for both the applications of the derivative test as well as for the midterm, as well as for the final and the AP test later on down the road. So we're going to start off here with this first question, which is just asking us to find the equation of the tangent line to the graph of f at the point where x is 1. So the first thing we need is to figure out what f of 1 is, right? Because we're going to need that. F of 1 is just going to be, well, we'll just plug that in, right? F of 1 is 2 times 1 minus 1, which is 1 to the 5th, which is 1 times 1 plus 1. So f of 1 is 2. Right? And then we'll just need to find f prime of x. So we'll find f prime of x by using the product rule. That'll be the first function, 2x minus 1 to the 5th, times the derivative of x plus 1, which is just 1. And then we'll add to that the derivative of 2x minus 1 to the 5th, which is u to the 5th, so 5u to the 4th, times the derivative of the 2x minus 1, which is just 2, and then times the original second function, which was x plus 1. So if we want to find f prime of 1, we need to plug in 1 to this, right? So f prime of 1 is going to give us 1 to the 5th times 1, or 1 here, plus 5 times 2 is going to be 10, and then times 2x minus 1 is 1 to the 4th, and then times 1 plus 1, which is 2. So it looks like that comes out to be 21. So we have a slope of 21 and a point of 1, 2. So we can immediately eliminate C, D, and E. We should really just immediately eliminate A also, because if the line has a slope of 21 and it goes through the point 1, 2, its y-intercept is not going to be 2. But just to confirm, we'll do y minus 2 equals 21. That's not 21. We'll do 21 times x minus 1 using point slope form. And when we simplify this down, we can see that we get y equals 21x minus 19. That eliminates A, and we get choice B. This second one is asking us a pretty similar question here, right? We want the tangent line. This time we'll have to take the derivative implicitly. So the derivative of x squared minus 3xy equals 10 is 2x. And then we'll take the derivative of minus 3xy using the product rule. So that'll be minus 3x times the derivative of y with respect to x. And then plus the derivative of negative 3x, which is negative 3 times y. And of course, equals 0, not equals 10, right? Because we have to take the derivative of the 10 on the other side as well. When we solve this for dy dx, we start with negative 3x dy dx is equal to 3y minus 2x, or, dy dx is equal to 3y minus 2x divided by negative 3x. So when we evaluate that at the point 1, negative 3, we end up with negative 9 minus 2 times 1, so negative 9 minus 2, over negative 3 times 1, which is negative 3, which gives us positive 11 thirds. So the equation should have a slope of 11 thirds. That eliminates A, B, C, and D. And we can see that if we use this point with point slope form, we would get y minus negative 3 equals 11 thirds times x minus 1. For our next one here, for number 3, we have a particle moving along a straight line. This is a motion problem. And we're given the graph of the particle's velocity. And we know that it's going to intersect at 0, k, and m. And it has horizontal tangents at j and l. We want to know, when is the speed decreasing? So there's two ways to look at this. One is to recognize that speed is just the absolute value of velocity, right? And so if I were to take the absolute value of this function, I would just get something like this. This part would just go away. And so if we want to know when the speed is decreasing, right now we have a speed graph. Well, speed is going to be decreasing from j to k, right, on this interval, and from L to M on this interval. So looks like that is choice C. The other thing you can do is you can remember that, we know that speed decreases when velocity and acceleration have opposite signs. So you can just look through here and see when that's true, right? Well, from 0 to k, the velocity is positive, but the acceleration is negative when the function is decreasing. So that would be between j and k. The velocity is positive, but it's going down. And then likewise, from k to m, the velocity is always negative, but it's increasing on L to m, which means the acceleration is positive when the velocity is negative, right? And so that's another way you could look at this. Two different ways to think. Our next one here, we have a particle moving along the x-axis. Its position is given by this function x of t is equal to t minus a times t minus b, where a and b are constants that don't equal each other. We want to know, when is the particle at rest? Well, the particle would be at rest when its velocity is equal to 0. So the first thing to do is find the velocity function. You can either distribute that out or you can just use the product rule. I'll use the product rule. So it's t minus a times the derivative of t minus b, which is just 1, right? Because b is a constant and t is the variable we're taking the derivative with respect to. Then we'll add to that t minus b times the derivative of t minus a, which is also just 1. So our velocity function is just t minus a plus t minus b, which would be 2t minus a minus b. If we want to know when that's at rest, we'll set it equal to 0. That gives us 2t equals a plus b, or a time of a plus b divided by 2, which is choice B. For our next one here, we have the position of a particle which is moving along the x-axis is given by sine of t minus cosine of t. We want to know what is the acceleration of the particle when its velocity is first equal to 0. So first we need to find a velocity function to figure out when the velocity is equal to 0. So the velocity function will just be the derivative of the position function, which is cosine t for the sine t part. And then the derivative of negative cosine t should be plus sine t. So our velocity function is just cosine t plus sine t. We'll set that equal to 0 to figure out when the velocity is first 0. That just tells us we want the cosine to be equal to the opposite of the sine. Well, we know that sine and cosine have very similar values at increments of pi over 4, right? Because the sine and the cosine of pi over 4 is root 2 over 2. Right? In the first quadrant, right, at pi over 4, they have the same sign. But in the second quadrant, sine is positive and cosine is negative. So we want the increment of pi over 4 in the second quadrant, which would be 3 pi over 4. So the time we're interested in is 3 pi over 4. We want the acceleration at 3 pi over 4. So that'd be v prime of t. So we'll take the derivative of cosine t plus sine t, which will be negative sine t plus cosine t. And we'll evaluate that at 3 pi over 4. Well, like we just said, the sine of 3 pi over 4 is root 2 over 2, so this is negative root 2 over 2, plus the cosine of 3 pi over 4, which is negative root 2 over 2. So that gives us, well, if we have negative root 2 over 2 and another negative root 2 over 2, that'd be negative 2 root 2 over 2, or just negative root 2. Option A. For our next one here, we've got a line tangent to the curve x to the 4th plus 3xy squared plus 5y cubed equals 9 at the point 1, 1. So first thing we'll do is just take our derivative, right? And we need to find the slope. So we'll do 4x cubed, and then the derivative of 3xy squared will be done with the product rule. So 3x times the derivative of y squared, which will be 2y dy dx, plus the derivative of 3x, which is 3, times y squared. And then plus 15y squared dy dx is equal to the derivative of 9, which is 0. We'll take all of our non-dy dx terms and bring them to the right-hand side, and we'll factor out the dy dx on the left. So we'll have 6xy from the 3x times the 2y, and a plus 15y squared from here is equal to the opposite of 4x cubed minus 3y squared when we bring those to the other side. So now we get dy dx is equal to negative 4x cubed minus 3y squared divided by 6xy plus 15y squared. Well, we wanted to evaluate this at the point 1, 1. So that gives us negative 4 minus 3 over 6 plus 15, right, which is negative 7 over 21, which is negative 1/3. So we can get rid of anything that doesn't have a slope of negative 1/3. That'd be A, D, and E, right? And then we just need to make sure that we're doing point slope form correctly. It's y minus the y value, so y minus 1 equals our slope, m, times x minus our x value, x minus 1. So not choice C. Looks like it comes out to be choice B. For our next one here, we have the position function for a particle is t cubed plus t squared minus 8t on the interval 0 to 10. We want to know when is the particle moving to the right. Well, a particle moves to the right when its velocity is greater than 0. Right? So we'll just take our velocity function, s prime of t is v of t, which will be 3t squared plus 2t minus 8. And then we'll need to factor this. So to get 3t squared, we'll need a 3t and a t. And to get 8, we either need 2 and 4 or 1 and 8. And there'll be one will be positive and the other will be negative. Now, we can probably just look over at the answer choices and say, it looks like it's probably going to be a minus 4, because 3 of the answer choices have a 4/3 in them. And so we'll try a minus 4 with a plus 2, and if we check that, that gives us 6t and minus 4t, which does give us positive 2t in the middle. Right? So we can kind of use the answer choices to help us figure out what that factorization is if we don't really want to think too hard about it. We end up with t equals 4/3 and t equals negative 2. I'm, of course, going to ignore t equals negative 2 because that's not between 0 and 10. So we'll make a sign chart with 0, 10, and 4/3 on it and see when it's positive. So between 0 and 4/3 would be something like 1. Well, 3t minus 4 is negative if t is 1, and t plus 2 is positive. So we're negative on that interval. But then we are going to be positive on this other interval. Like if we plug in, 7 here, we're going to get a positive times a positive, which is a positive. So we want the interval from 4/3 to 10. Our next one here, we're looking at the equation 3e to the negative 2x, and we want the equation of the normal line to the graph at ln2. So in order to write the equation of a normal line, we first need to know the slope of the tangent line. And then to find the normal line, we want the opposite reciprocal of the slope of the tangent line. Right? The slope of the normal line is the opposite reciprocal of the slope of the tangent line. We're also going to need to figure out what our function actually equals at ln2. So 3e to the negative 2 ln2, we can rewrite this as 3e to the ln of 2 to the negative 2 power, right, by bringing that coefficient on the logarithm inside as an exponent. Or that's the same as 3e to the natural log of 1 over 2 squared, or 1/4. And e to the ln of 1/4 should just be 1/4. So this is equal to 3 times 1/4, or 3/4. So the point we're looking at is the point ln 2, comma 3/4. So that's our point for point slope form. Then we need to find the actual slope. So we need the derivative y prime. Well, the derivative of 3e to the negative 2x is just 3e to the negative 2x times the derivative of negative 2x. That's the chain rule part. So we have negative 6e to the negative 2x. If we evaluate that at ln of 2, we have negative 6e to the negative 2 ln 2. Well, we do the same process with the negative 2 ln 2 as we did before. That becomes the same as negative 6e to the ln of 1/4, or we end up getting negative 6 times 1/4, which is negative 3/2. And so be careful not to immediately jump back to the answer choices and eliminate the ones that don't have a slope of negative 3/2, because remember, we're looking for a normal line, which means that our slope should be 2/3, which means we're going to eliminate anything that is not a slope of 2/3. So we should end up with, right, the slope of the normal line being positive 2/3, which gives us y minus 3/4 equals 2/3 times x minus ln 2. We'll just add the 3/4 to the other side and see that it's not choice B, it is choice A. Our next one here, we have a velocity function given to us. We want to know when is the speed increasing. So we want to know when do velocity and acceleration have the same sign, right? Speed increases means v of t and a of t have the same sign. They're either both positive or they're both negative. So we need to figure out the signs of the velocity first. So we'll factor t squared minus 3t minus 10, right? We'll say v of t is equal to, that factors to t minus 5 and t plus 2. When I set that equal to 0, we have t equals 5 and t equals negative 2. We'll ignore t equals negative 2 because it says positive values, right? So we'll make a sign chart for our velocity with 0 and 5 on it. Seeing that between 0 and 5, put in something like 2, we get a negative and a positive, which makes it a negative velocity, but something more than 5 makes it a positive times a positive, so we have a positive velocity. Right? So this is our velocity sign chart. Then we'll go through and we'll find the acceleration function. So the acceleration function is just the derivative of the velocity function, which gives us 2t minus 3. When we set that equal to 0, we get t equals 3/2. So we'll make a sign chart for our acceleration function, plugging in something between 0 and 3/2, like 1, makes our acceleration negative here. But something more than 3/2, like a billion, makes 2t minus 3 positive, so our acceleration is positive. So we're looking for the overlap here for when they have the same sign. Well, they're both negative from 0 to 3/2, right? And then they're both positive again after 5. So it looks like, right, the overlap is 0 to 3/2 here, right? Because this is 0 to 3/2, right? Is in there. And then we're positive here after 5, and this one is also positive after 3/2, so it's positive after 5 as well. So we're looking at 0 to 3/2, and when t is greater than 5. All right, our next one here, we have a tangent to a parabola. So that's y equals ax squared. At x equals p, we want to know when it intersects the y-axis. So the first thing we need is we need a point, and we need a slope to write the equation of the tangent line. So the point would be the point p comma something. So y evaluated at p would be just a p squared. So the point we're looking at is the point p, a p squared. Then we need the slope of the tangent line. So we need y prime. Y prime is just equal to 2ax. And if we evaluate that at x equals p, we get a slope of 2ap. So we should be able to write the equation of our tangent line. Our tangent line's equation should be y minus ap squared equals our slope 2ap times x minus p, right? Just using point slope form. And then the question asks us, when does this intersect the y-axis? Well, something has a y-intercept when its x value is equal to 0, right? It intersects the y-axis if x is 0. So we'll just plug in 0 for x, and we will solve then for y. So we have y minus ap squared equals 2ap times 0 minus p, which is just negative p. So we have y minus ap squared equals negative 2ap squared, or y is equal to just negative 1ap squared. So the coordinates at that point are 0, comma, negative ap squared. Obviously, we get rid of those ones, and 0, negative ap squared is choice C. For number 11 here, we have the equation of the line tangent to y equals 4x cubed minus 7x squared at x equals 3. So this is just a plug in 3. Y of 3 should be 4 times 3 cubed minus 7 times 3 squared. Well, 4 times 3 cubed minus 7 times 3 squared. 3 cubed is 27 times 4 is 108. And that'd be minus 63. So it looks like that comes out to be 45. And then we need the slope of the tangent line. So we'll take our derivative. Y prime is 12x squared minus 14x. We'll evaluate that at x equals 3. So 12 times 3 squared minus 14 times 3. Well, 12 times 3 squared is also 108. And then 14 times 3 is 42. Subtract those to get a slope of 66. We're talking about a tangent line, so it's not the one with the opposite reciprocal slope. We'll just write it out in point slope form. Y minus 45 equals 66 times x minus 3. And it looks like that is already written up here. That's choice B. For number 12 here, we're again looking for the equation of a tangent line. We've already got the point, so we'll just take the derivative. 18x plus 32y dy dx is equal to 0. So if we solve this for dy dx, we'll have 32y dy dx is equal to negative 18x, or dy dx is negative 18x over 32y. If you want to, you can simplify that down to negative 9x over 16y, just to make the arithmetic easier in advance if you want. We'll evaluate that at the point 2, negative 1, which will be negative 18 over negative 16, which reduces down to 9 over 8. So our equation of our line should be y minus negative 1 equals 9/8 of x minus 2. Now, these are all in standard form. So if we multiply everything by 8, right, that'll give us 9y plus 9. If we multiply by 8, that'll give us 8y plus 8. I was already trying to distribute a 9. Equals 9x minus 18 over here. And then we just want to get everything to one side. And I guess we'll just bring it over to the left-hand side, because that looks like it's going to give us the right answer here. So we're going to end up with 9x minus an 8y if we bring the 8y over. And then negative 18 minus 8 will be minus 26 is equal to 0. So 9x minus 8y minus 26 equals 0 is choice B. Our next one here, we have a particle's position given by t cubed minus 6t squared plus 9t. We want to know the acceleration at t equals 4, so we just need a second derivative. Right? S prime should be v, which will be 3t squared minus 12t plus 9. and v prime will be a, which will be 6t minus 12. If we evaluate that at 4, we get 24 minus 12, which is just 12. For number 14 here, we've got a function negative x cubed plus 75x. We want to know when is the function decreasing. So a function decreases when its derivative is negative. So we'll find the derivative, negative 3x squared plus 75. If we set that equal to 0, we end up getting negative 3x squared equals negative 75. Or x squared equals 25, or x is positive or negative 5. And so we potentially have a change in increasing to decreasing at 5 and negative 5. So we will then go right ahead and plug those in. Some value in between negative 5 and 5 would be 0. If I plug 0 into my derivative here, I get a positive number, so my function is increasing on that interval. If I plug in something like a billion, then negative 3 times a billion squared is such an astronomically large negative number that when I add 75, we're still negative. And the same happens if I put in something like negative a billion. So we can see that our function is decreasing on the interval from negative infinity to negative 5, and then again from 5 to infinity, right? Because it is decreasing on the interval on which the derivative is negative. For our next one here, we're looking at a limit. This limit, if we try to plug in pi over 4 to this, we end up taking the tangent of pi over 2, which we know to be infinite, right? And the same with the secant, right? The secant of pi over 2 is also infinite. And so we'll want to use L'Hopital's rule for this, noting that if this was a free response question, we would definitely want to write out those limits separately. But since it's multiple choice, if this was the AP test, it wouldn't really matter. So we'll just take the derivative using L'Hopital's rule here to find this limit. We'll get the limit as x approaches pi over 4. The derivative of 2 tangent 2x is 4 secant squared 4x. Not 4x, 2x. Sorry. Because that 2 doesn't change in there, right? We just use the chain rule to multiply a 2 out in the front. And then the derivative of 1 is 0, and the derivative of 3 secant 2x, the 2 gets multiplied out, it's 6 secant 2x tangent 2x. And we can simplify this. In fact, we're going to do a couple simplifications here. First of all, the 4 over the 6 is just a 2 over a 3. But I can also cancel out one of the secant 2x's in the numerator with the secant 2x in the denominator. And then now we saw one in class like this where if we kept working with this, it sort of became an infinite loop. So we need to just go right ahead and simplify the trig even further. Right, we're going to write 2 over cosine 2x over 3 sine 2x over cosine 2x. And then we can cancel the cosine 2x's. And so we end up with the limit as x approaches pi over 4 of 2 over 3 sine 2x, which is just 2 over 3 times the sine of pi over 2. Well, we know that the sine of pi over 2 is 1, so this is just 2 over 3. All right, our next one here, we have the function x over L in x. And so we want to figure out when we might have a local minimum. So we need to take the derivative of this. So f prime of x, we'll use the quotient rule. So it's the denominator, natural log, times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator. The derivative of natural log is 1 over x, all over the natural log of x squared. And so what we end up with is the natural log of x minus 1 over the natural log of x squared. And we want to know when does this equal 0 and when is this undefined? Well, the first thing we'll note is that it's only undefined when x is equal to 1, right? That's what makes the denominator undefined. But also, that makes the denominator 0. But that also makes our original function undefined, right? We can't actually put in x equals 1 into this function. There's no point at x equals 1. Therefore, there's no possibility of having a local minimum at x equals 1. So we can eliminate choice A right off the bat. Can't have a minimum if the function doesn't exist there. Now, I'll write that out. Undefined at x equals 1, but not in domain. We'll still put that on our sign chart because something could be happening there. But we then will set, if there were domain values to the left of 1, we could have like a discontinuity there where the function changes from increasing to decreasing. But we'll just cut off our sign chart there because that's the end of our domain. So then we'll set natural log of x minus 1 equal to 0, giving us natural log of x equals 1. Well, the natural log of e is 1, so x is e. So our sign chart should look like this. We should have a 1 here and an e here on our derivative sign chart. And so we'll plug in a value between 1 and e, something like 2. If we plug in 2, the denominator down here is always going to be positive, but something something less than e, like 2, is going to make natural log less than 1, which means that something less than 1 minus 1 is going to be negative, so we're negative down here. And then something more than e, like 1 billion, is going to make us a positive in the numerator. So our function decreases, then increases, which means we have a minimum at e. So we can eliminate choices b and c, and then we will do f of e, which is e over the natural log of e, or just e over 1, to see that the point that we're doing this at is at e, comma, e, which is choice D. So for our next one here, we've got a function g of x, which is x e to the power of kx, where k is just some constant. We want to know for what value of k does g have a critical point when x is 2. Well, critical points are when the derivative is equal to 0. So first of all, we just need to take the derivative of this. So g prime of x, we will get by taking the derivative using the product rule. So that'll be x times the derivative of e to the kx, which is e to the kx, times the derivative of kx, which is k. Then we'll add to that the derivative of x, which is 1, times e to the kx. So we'll factor this out so that it's easier to set equal to 0. We'll factor out the e to the kx from both of them, leaving us with x times k plus 1 equals 0. Well, e to the kx was never going to equal 0, but x times k plus 1 could equal 0. Right? And so we want to know, when does x k plus 1 equal 0? Well, when x is 2. So really, it's when does 2k plus 1 equals 0? Well, that would be when k is equal to negative 1/2. For our next one here, we want to know, when is the function h concave up? Now, a function is concave up when its second derivative is positive. So we just need to find the second derivative. So h prime of x, our first derivative, will be x cubed minus 6x using the product rule. And then our second derivative will be 3x squared minus 6. We'll set that equal to 0. We could factor out the 3 if we want, giving us x squared minus 2. And then we can see that that happens at plus or minus root 2. So the only place where this might be changing concavity is at positive or negative root 2. So we can eliminate the ones with the root 6's. Right? And we'll make a sign chart here with negative root 2 and positive root 2 on our second derivative. Something between those would be 0. If I plug in 0 to my second derivative here, I get a negative. If I plug in something more than 2, like 1 billion, I get a positive. Same with negative 1 billion, because negative 1 billion squared is positive. So we can see that we are concave up when the second derivative is positive, which would be from negative infinity to negative root 2, and also from root 2 to infinity. So looks like that is choice A. For number 19 here, we have we want to find the height of a cylinder that has a volume of 250 pi, but with minimum surface area. So to start with, we'll write out a formula for the surface area of a cylinder. That should be, we'll draw a picture of the cylinder first. And here's your cylinder. Its surface area should be two circles, right? The two bases, which would be 2 pi r squared. And then plus the lateral surface area, right? So each of these is pi r squared. And the lateral surface area, which is the circumference of the base, 2 pi r, times the height. So our surface area should be 2 pi r squared plus 2 pi r h, right? We'll draw a little arrow down here. That one's also pi r squared. And so we have 2 pi r squared plus 2 pi r h. We can't really deal with that unless we get rid of the h variable or get rid of the r variable. And so what we need to do is we need to use the fact that the volume is 250 pi. And we know volume of a cylinder should be the area of the base, pi r squared, times the height. So I can solve that for h, right? H should be 250 pi over pi r squared, or just 250 over r squared. So I can replace my h in my original surface area equation with 250 over r squared. And as we rewrite this, then, we end up with our area being 2 pi r squared plus 500 pi r over r squared, which is r to the negative 1. Or we could write it over r. I'm going to write it as r to the negative 1 so that when I take my derivative right now, we end up using the power rule. That's not an x, that's a pi. 4 pi r for the derivative of 2 pi r squared, and then minus 500 pi r to the negative 2, or 500 pi over r squared. We'll want to get a common denominator, which will be r squared, which will give us 4 pi r cubed minus 500 pi over r squared. When we set the denominator equal to 0 to see when it's undefined, we get a radius of 0, which of course makes no sense in the context of the problem. So we'll just set the numerator equal to 0. 4 pi r cubed minus 500 pi equals 0. Well, if we add the 500 pi over to the other side, and then divide 500 pi by 4 pi, we get r cubed equals 125, or a radius of 5. Now, we do want to check and make sure that that makes a minimum value for our surface area, right? So r equals, get rid of that. Both of those look bad. 0 here and 5, right? So if I put in something between 0 and 5, like 1, right, we get 4 pi minus 500 pi, clearly negative. Something more than 5, like a billion, this is clearly a big positive, minus 500 pi, which is going to be positive. So it is a minimum when r is 5. Of course, r being 5 is not the answer to the question. We wanted to know the height, right? Well, height, as we said earlier, was equal to 250 pi over pi times the radius squared, right? Well, the pi's cancel, and 250 over 25 is just 10. So the height of a cylinder that has a minimum surface area with a volume of 250 pi should be 10 feet. All right, we want to approximate the change in the volume of a tetrahedron, right? So 4 equilateral triangles, if the side length is increasing from 10 to 10.1 inches. So this is like a linearization differentials type problem. So the volume is a cubed over 6 root 2. A is the length of the side. So all we have to do is just say dv is equal to 3a squared over 6 root 2 dA. Just take the derivative of both sides as a differential, right? The small change in the volume is equal to the slope of the tangent line of this volume equation times the change in the A. Well, A is starting at 10, and it's increasing by 0.1, so dA will be 0.1. So we'll just plug those in. We have 3 times 10 squared over 6 root 2 times 0.1. Well, 3 times 100 times 0.1 is 30. So we have 30 over 6 root 2, which would just be 5 over root 2 cubic inches, which is choice C. For our next one here, we've got a particle moving along the x-axis. The position is 6t cubed minus 2t, and the acceleration of the particle is what we're looking for at t equals 6. So we just need a second derivative. Velocity should be x prime. That'll be 18t squared minus 2. And acceleration ought to be v prime, which will just be 36t. If we evaluate 36t at t equals 6, 36 times 6 is just 216. All right, here we have a function that is continuous and differentiable on the interval from 0 to 10. And so our table is giving us values of the function, its second derivative, our first derivative and second derivative, both at 2, 3, and 4. And we want to know which is true. So we got a lot of different options here. So if we look at option number 1, does f have a local maximum at x equals 2? Well, in order to have a local max or a local min, the derivative must be 0 or it must be undefined. So f prime of 2 would have to be 0 or undefined. Well, in the chart, f prime of 2 is 3. So nope, can't be 1, which means we'll eliminate choice D. For number 2, f of x has a local maximum at x equals 3. Well, first of all, the derivative would have to be 0, which it is. Okay. And then the only way to figure this out from a chart would be to look at the second derivative of it at x equals 3. Well, the second derivative is positive, which tells you that the function at that critical value is concave up, which means that it has a minimum. So this function actually has a minimum at x equals 3, not a maximum at x equals 3. So we'll eliminate choice, the one with 2. So anything with 2 in it can be eliminated. Then we'll look at 3. Number 3 says it's a possible point of inflection at 2, 1. So yeah, 2, 1 is a point. And the second derivative is 0 there, which means, yes, it is a possible point of inflection. So that's true, which means we can eliminate anything that doesn't have number 3 in it, which that'd be B. So it must be choice E, but we'll go through and make sure that we understand why the rest of these are true. So for number 4, it says there must be a point of inflection on the interval 3 to 4. Well, if the function is continuous and differentiable across all of these things, and the second derivative goes from a positive to a negative, it must have gone through 0 to go from 1 to -2, which means the second derivative must have changed signs between x equals 3 and x equals 4. So yes, there must be a point of inflection because the second derivative changed signs. Then number 5, right, says that f of x is increasing at x equals 2. Well, a function increases when its derivative is positive. So at x equals 2, f prime is positive. So yep, must be increasing. And option 6 is f of x is decreasing at x equals 4, which means the derivative has to be negative, which it is. So we can see that 3, 4, 5, and 6 were all true. 1 and 2 were not true. And so our answer is choice E. For our next one here, we've got the interval 0 to 2 pi, and we want to know when is the sine of the cosine of x increasing. Well, the sine of the cosine of x would be increasing when its derivative is positive. So we need to find f prime of x. That's sine of u. So the derivative of sine of u would be cosine of u, cosine of the cosine of x, times the derivative of cosine, which is negative sine of x. So we want to know, when is this thing positive, right? When is this derivative positive? So we just need to set it equal to 0 first to figure out where it might change signs. And now we know that it's going to change signs when sine of x is equal to 0. So that'd be when x is 0 or pi or 2 pi. And then if we think about the cosine of x, well, the only time cosine of something is equal to 0 would be at pi over 2 or at the cosine of 3 pi over 2, right? Which means that to make cosine of x equal 0, we would have to take the cosine of pi over 2 or the cosine of 3 pi over 2, which would mean that cosine x would have to equal pi over 2, or cosine x would have to equal 3 pi over 2. Well, the output of cosine is always between -1 and 1, and both pi over 2 and 3 pi over 2 are outside of that range, so that's never true. So these are the only places where it might change signs. So we'll put 0, pi, and 2 pi on our sign chart. And if we think about something between 0 and pi, right, the sign of something between 0 and pi is always going to be positive. So when I multiply it by a negative for the negative sign, it's going to become a negative. And if we take the cosine of anything, we're going to get something that's between -1 and 1, right? And something between -1 and 1 is going to either be in the fourth quadrant, or it's going to be in the first quadrant. So if I take the cosine of something that is in the first or the fourth quadrant, I always get a positive. So this is always positive no matter what. And so therefore, we can just say, well, it's a positive times a negative, which makes this a negative. And then if I put in something between pi and 2 pi, so a third or a fourth quadrant angle, the negative of the sign of something that's in the third or the fourth quadrant would be the negative of a negative, which would be a positive, which would tell us that this function is increasing on the interval from pi to 2 pi, right? Because the derivative is positive on that interval. So our next one here is another limit. We got the limit as x approaches 4 of sine pi x over 2 over x cubed minus 64. This is the sine of 2 pi, which is 0, over 64 minus 64, which is 0. So this is a L'Hopital's rule derivative problem. If this was on the free response, you'd write out the limit at the top and the limit at the bottom, but I won't do that because this is just multiple choice and it doesn't matter. They won't be checking your work on that. So the derivative of sine pi over 2x will be pi over 2 cosine of pi over 2x. And the derivative of x cubed minus 64 will just be 3x squared. And so all we have to do is just now evaluate this at 4. So we have pi over 2 times the cosine of 2 pi over 3 times 4 squared. Well, the cosine of 2 pi is just 1, so this is pi over 2 over 3 times 16, which is 48, which gives us pi over 96. And for this one, we have the graph of the second derivative. We want to know, when is the function concave down? Well, a function is concave down when its second derivative is negative, right? If f double prime is less than 0. Well, that'd be here and here. So from -2 to -1. And again from 1 to 3. Or if we were to write that out not in interval notation, right, it would be -2 is less than x is less than -1, and x is less than 1, less than 3. So answer choice E. So that's it for the non-calculator questions here. So now we're going to take a look at a couple of calculator multiple choice questions. And the first one here is just saying the first derivative of a graph is given by x minus 4e to the negative sine 2x. We want to know how many points of inflection the graph has on the interval 0 to 2 pi. Well, a function has points of inflection when its second derivative changes signs, right? When its second derivative goes from positive to negative. In other words, that would be whenever your original derivative, right? Whenever your first derivative has a local max or a local min. So what we'll do is we'll just graph x minus 4e to the negative sine 2x on our graphing calculator. Right? So we had x minus 4e to the power of negative sine 2x. And we'll graph that on our graphing calculator. And we'll look for the number of turning points between 0 and 2 pi. Well, it'd be nice then to change our window here, make our x minimum 0. So we hit window and change x min to 0 and x max to 2 pi. And when we do that and look at the graph, we can just count the number of turning points to determine the number of points of inflection this has. It looks like it has a maximum over here right around 1, another maximum down here, a minimum down here, a maximum over here. Or that wasn't 1 at the beginning, but a third one here, and a fourth one right here. So it looks like it has 4 maxima or minima on the original derivative, and so we will have 4 points of inflection for the graph. For this next one, we're given f prime. We want to know when f has a maximum. Well, f has a maximum if f prime goes from positive to negative, right? Because then f increases and then decreases. So we just need to graph our derivative and see when it goes from positive to negative. So we will we'll change our window back to what it was originally. Zoom option 6. And then we'll go into our y equals screen, clear out that equation, graph our new equation, which is the square root of x to the 4th power plus 1. And then outside of that, plus x cubed and minus 3x. And so we are looking for when this goes from positive to negative, right? So when the derivative goes from positive to negative. So it looks like that's somewhere over there between 0 and 1. We'll hit second and then trace, and we'll choose option 2 for 0. And we want to get kind of close to where that x-intercept is, but make sure we're still to the left of it. Right? So we're definitely to the left of it there. Hit enter, and then move over so you're to the right of it and hit enter again. Then it'll say guess. Hit enter a third time, and we can see that that happens at about 0.35013775, which would be choice C. For number 28 here, it wants us to use Newton's method to approximate the solution to this equation. So what we'll do first is we'll get it equal to 0. So that'll be x cubed minus 3x minus 4 is equal to 0. And then we'll try and come up with a good starting point here. It seems to me like f of 2 is equal to, let's see, f of 2 should be 8 minus 6 minus 4, which is negative 2. And f of 3 should be equal to 27 minus 9 minus 4, which ought to be 14. So it changes signs between 2 and 3. So a good starting value is going to be 2.5. Right? And we're going to use the formula x sub n plus 1 is equal to x sub n minus f of x sub n, which will now be x sub n cubed minus 3x sub n minus 4, all over f prime of x sub n. Well, if this was f, then f prime is going to be 3x squared minus 3. So 3x sub n squared minus 3. And so I'm not going to bother to write all these out this time because this is a multiple choice question. If this was my test, you would definitely want to write them all out for a non-multiple choice question. But we'll start with 2.5 as our first guess. So we'll just go to our home screen here on our calculator. We'll put in 2.5. And then anywhere we had an x sub n, our formula, we'll use second and the negative sign for answer. So x sub n minus, we'll use the nice alpha and x to give us this fraction bar. And then we have the x sub n to the third power minus 3x sub n minus 4 all over 3x sub n squared minus 3. And we'll go through a few times here until we end up getting values that repeat. So there's x sub 1, x sub 2, x sub 3, x sub 4, and it looks like x sub 5 ends up being the same. So 2.195823345, which ends up being choice C. Just two more of these here to go. So for number 29, we want to use differentials to approximate the change in the surface area of this torus, right? So it's just like a donut, basically. If the major axis, so the larger radius, goes from 3 to 3.004, and the minor axis goes from 2 to 2.004 as well. And then the surface area of it is pi squared times the major axis squared minus the minor axis squared. So, I think we've cut off our value down here. We can't quite see choice E, which is 0.0789568.307, just to make sure we can see that value down there. So the correct method to use here is just going to be a differential. Right, so we're going to do dA, the change in the surface area, is pi squared, which isn't going to change, times 2 big R d big R minus 2 little r d little r. And big R is 3, and little r is 2, and d big R, it's going up by 0.004, and d little r is going up also by 0.004. So we should just get pi squared times 2 times 3 times 0.004 minus 2 times 2 times 0.004. Well, looks like if we could just kind of quickly simplify that a little bit, right? I mean, we have 6 times 0.004 minus 4 times 0.004, which ought to just be 2 times 0.004. So we have pi squared times 2 times 0.004. If we go into our calculator here, we've got, what did we say? We had pi squared times 2 times 0.004, which should be 0.0789568.352. Which looks like it was choice B. And our last one here, number 30, we're going to use the linearization for the fourth root of x to approximate the fourth root of 16.003. So our function f is x to the 1/4, which means that f prime of x is 1/4 x to the negative 3/4. And the x value we care about is 16.003, and the a value is going to be 16, because we know that we can take the fourth root of 16 really easily. The fourth root of 16 is just 2. And the formula, of course, we'll rewrite the formula. It's f of a plus f prime of a times x minus a. And that's the formula for linearization. So we will go in and we will just put in our fourth root of a. So that fourth root of 16 we just said is 2. And then plus f prime of a. So that'll be 1/4 of 2 to the 3, or not 2, but 16 to the 3/4 power. Right? And then we'll multiply that by 16.003 minus 16. That doesn't really look much like a 3. That's better. All right, so now we have 2 plus, well, the 16 to the 3/4 power, right, should be, if we do 16 to the 3/4 power, the fourth root of 16 is 2, and then 2 cubed is 8. So we have 1 over 4 times 8, or 1 over 32, times 0.003. So we'll just use our calculator and do 0.003 divided by 32. And we'll add 2 to that. And it gives us 2.00009375, which is choice B. And that is the end of the walkthrough here for our applications of the derivative multiple choice homework assignment.